Thank you very much for your kind introduction. There's only one thing missing, which is a clicker to advance the slides. What I'm going to talk to you about, something dear to all of our hearts, which is how we can actually really deliver the value promised by these sorts of AI approaches that we've been hearing so much about today. I'm going to talk a little bit about what it takes to maximize the impact of AI in our drug discovery projects. And to illustrate that, I'm going to use an example of our platform, Segall, and really think about what it means to deliver value in the context of drug discovery. And then I'll sort of wrap up with a few conclusions and hopefully leave some time for some questions at the end. But before I go any further, I actually want to give you a disclaimer. AI is not magic. At the crudest level, AI is just a very effective way at identifying patterns in complex data. Once you've done that, you can do a number of things. You can find things that are like things it's seen before. Given a picture of a dog, it can find more pictures of dogs. Or you can make a prediction. You can actually say, I'm looking for, give it a new picture and have it say, oh, this is likely to be a dog based on things I've seen before. Or you can generate new things. You can give it the prompt, give me a picture of a dog, and it will generate a completely new hypothetical picture of a dog. And that's at heart what we're doing in all of these applications. So if someone's making a claim about an AI algorithm that seems too good to be true, it may well be. You should be skeptical. You should be cautious about that. And in particular, don't expect to just sort of dust a bit of AI over your drug discovery projects and for it to magically transform the outcomes. So what does it take to actually maximize the impact of AI in drug discovery? Well, it all starts with an algorithm, of course. And one thing we need to be cautious of here is that the data we deal with in drug discovery is often very different from that in the domains in which these methods are applied. We heard, for example, Dave in the panel talking about the fact that data we have is extremely noisy. The data sets we have are also orders of magnitude smaller than many AI organizations. But once we have an algorithm, we need to prove it works. So proof of concept. In an ideal world, I'd run the same project twice, once with the AI method and once without, and compare the outcome. Well, that's not sufficient. We need to do that a statistically significant number of times to check that it really does work and it wasn't just luck. And I've never met a company that wants to do that, unfortunately. So what we're stuck with doing typically is looking at a retrospective analysis and running the sort of the counterfactual version of a project if we had applied the AI approach. Or we can run it truly prospectively and compare against some sort of industry benchmark to see if we're doing better than sort of on average, if you like, across the industry. But once we've convinced ourselves that it works and it does something useful, then we've got to put it in the hands of the practitioners, in the hands of the medicinal chemists, the biologists, and so on. We need to think about deployment. It needs to work robustly, not just with the perfect idealized data sets that we've prepared to build and validate the method, but with data we're generating in the real world. And it needs to be accessible. It can't be some fancy command line script that the data scientists are really happy with, but it's got to be presented in a way that is intuitive and just makes sense in terms of the decisions that project teams are making. And then finally, we've got to think about organizational change. We can't simply continue to do drug discovery the same way. We've seen some great examples of talks already today about the way that these organizations are working to really drive the impact of AI on the projects that they're working on. So to illustrate this, I'm going to talk about our platform, Segall. So let me just tell you what that is in just a few sentences. So Segall is a proven and deployable AI platform. I hope I'll convince you of that as we go through here. And what it does is it empowers drug discovery teams to go from their concepts to a candidate compound faster. It does this in a few ways. It uses early stage data to much more confidently and accurately predict the outcome of those late stage expensive experiments that we're doing. It also helps to choose the most valuable experiments to do now that will help us to better guide our compound progression and improve the return on that experimental investment. And it can look into existing data and find those hidden opportunities caused by missing, uncertain, or just plain incorrect data. We know we've got these dreaded false negatives hidden in our data. How do we actually find them and rescue those valuable opportunities? So let's talk about the algorithm. Some of you will be very disappointed because I'm not going to put lots of equations on the screen. Some of you will be delighted because I'm not going to put lots of equations on the screen. But I will show you the publications at the end. So if anyone really wants to dig into the nitty-gritty, it's all out there, it's all published. But essentially, what Segall does is it applies a method called deep imputation to the data we have in drug discovery. What does that mean? Well, this is a typical sort of matrix of experimental data we might have. So compounds on one side, experiments across the top, and the little blue squares represent the measurements that have actually been made. And the first thing you'll notice, of course, there's lots of white space here. We cannot run every experiment on experiment on any one compound, and we cannot run every compound through any experiment. We've got white space here. Now, I've organized these experiments from the left-hand side, which is an early stage, typically in vitro experiments, biochemical activity, ADME, physicochemical properties, and so on. These experiments are higher throughput, cheaper to run, and as we move to the right-hand side, we move downstream to the late stage, typically even in vivo experiments, or maybe before that, phenotypic experiments. These are, of course, lower throughput and more expensive to run. Now, that's a pity because, of course, it's these experiments on the right-hand side that are most informative. That's where we'd like to have more data to find those good compounds that are going to be successful clinical candidates. And even more unfortunately, those are the properties that are hardest to predict using conventional QSAR methods. Why is that? Well, these are very complex properties. There are many different biological factors that will contribute to the outcome, maybe an in vivo disposition or an in vivo efficacy, and relating each of those factors back to the structure of the compound and then combining all of those into a prediction of the overall outcome would need a vast amount of data. And the catch-22 is, that's where we have the least data because it's expensive and time-consuming to generate it. So imputation approaches this in a different way. We can still use structural descriptors, but it also recognizes that this early stage data we generate contains very valuable information with which to much more accurately predict those downstream complex endpoints. So the idea of imputation is to sort of sweep across this matrix and fill in those blanks with these purple squares. And what we've shown in many publications and many examples is that these imputed values are much more accurate than conventional QSAR methods can achieve, particularly for those downstream complex and expensive endpoints. Now, we can go further than that because instead of just predicting a single value for each of these data points, we can actually predict a probability distribution over values. So sometimes you see these very sharply peaked distributions like the one at the top here. That's the model saying, yeah, I've got a lot of evidence for this. I'm confident in that prediction, a small error bar. In other times, you see these sort of broad smeared out distributions, and that's saying, look, I need a bit more data. I'm not yet, I've got a big error bar on this prediction. And what we've shown again in many examples, published examples, is that the model's estimate of uncertainty correlates very strongly with the observed accuracy. So we know when we can trust the predictions, we know when we need more data in order to justify that. Now, in building these models, what it's doing essentially is learning patterns. It's learning about these relationships between these different experimental endpoints, even though that data is very sparse. So it can also give us very valuable insights into what is sort of driving these outcomes downstream, mechanisms of action, adverse outcome pathways, for example. What are the most important early stage data to generate that will inform those downstream predictions? And so we can go further and we can actually say, well, if you actually measure these points, the little red squares here, and feed those back into the model, it will improve the accuracy of predictions and hence allow us to make even better predictions of those outcomes so we can choose the best compounds, again, maximizing the return on that experimental effort. So just to sort of summarize that, here's my matrix, if you like, compounds and experiments. I've added one thing, which of course we have the compounds we've synthesized and have some data on. We also have an almost infinite list of possible compounds we might like to make. And what conventional QSAR models are very good at is actually this vertical axis. Where we have enough data to make predictions, we can actually move down that and help us to choose what compounds we should make next. Sorella can do that as a byproduct of building these models. But where it really adds value is this horizontal axis. Thinking about the progression of compounds. Which are the best compounds to progress? Are there any opportunities hidden in here that we haven't yet measured, or maybe we have a false negative that we should go back and look at again? And what are the most valuable experiments to run next that will best inform that progression of those compounds? So that's the algorithm. Well, how do we know it works? And here, really, what I want to think about is not just working in a statistical sense, but how it actually demonstrates value in drug discovery. Because conventionally, when we're looking at these machine learning methods, we think about lots of statistics to compare. We look at coefficients of determination, or squared correlation coefficients, or root mean square error, or mean absolute error, or p-value in statistical tests. But what does that really mean? If I tell you my model's got an R-squared of 0.75 versus 0.7, what does that mean? Does it make a difference? The real value of these methods, and we've seen some lovely examples in presentations previously, is actually in finding the same high-quality compounds faster and cheaper, so fewer compounds synthesized, fewer experiments run, shorter timelines. Or the other side of that is finding something even better, finding valuable compounds that we otherwise have missed, maybe by exploring chemical space more rigorously or going back and finding these missed opportunities. So let's look at some examples of this. Here's an example of using early stage data to confidently predict those late stage expensive outcomes. In this case, pharmacokinetics in an animal study. So what we've done here, this is working with one of our collaborators, is we took a project and we took a particular time point and we look at how that project ran going forward. That's the blue curve here. This is the true chronological progression of that project. Here we're looking at the number of compounds tested in vivo PK studies. On the y-axis is the number of compounds that met their bioavailability criterion. So this, if you like, is your return on the y-axis and investment on the x-axis here. But we could ask ourselves a different question, which is, okay, if we'd taken the data available at that time point and built a model and use that to predict these downstream, the PK studies, and how could we have actually improved our ability to find those bioavailable compounds? And what you can see here in the orange curve is we actually find those compounds that meet the project criteria much, much more quickly. And in fact, we could have saved 95 PK studies. Now, what does that mean in real terms? Well, if we take a conservative estimate of about £5,000 for an in vivo study, then we're saving about $500,000 for this project in identifying the same bioavailable compounds for their projects. Now, again, we can take this further. This is another project with a different collaborator. Here we were looking at in vivo efficacy in an animal model. And again, we can reduce the number of compounds to find the same efficacious compounds. Again, here's my sort of two curves, the project progression in blue versus the prediction sort of ranking of those compounds. Save about 2/3 of the number of compounds to achieve the same outcome. But we can actually say, of the data generated experimentally, how much value is that actually adding? And so if we ask the model what it wants, to anthropomorphize a little bit, but what does the model want to make these predictions? You can see some of these experiments that are being performed, it's saying, yeah, I need all that data. Give me all the available data you got because it's really valuable. But there are some experiments that saying, actually, that adds no value at all in finding these efficacious compounds. So we could have actually reduced by the number of experiments on those compounds by about 43%, giving a savings of about 80% to achieve the same results. In addition, it actually found some additional compounds that were predicted to be high efficacy. Unfortunately, the project hasn't gone back yet to check those, but there are potential new opportunities. But to achieve the same results, you can imagine you could run over 4 times the number of projects for the same resources if you were to take this sort of approach. But again, it's not just about finding the same compounds for less effort. What about opportunities we might have missed? So here's an example where we're looking for hidden opportunities caused by missing, uncertain, or incorrect data. We went back to this company's existing collection, over 30,000 compounds. We identified 312, which is saying, look, I know you've measured it, but that looks really unlikely. Go back and check it again. Now, obviously, the human has to look at these, of course, and there's some compounds that there's just no good reason to progress for other reasons. Maybe other properties or something like that. So they narrowed that down to 17 of those, which are retested, and actually found that 7 of those were indeed active, over a 40% hit rate. And you can imagine that recovering these existing compounds already in the company's collection is much higher return from the existing compounds. And you can imagine what it would cost to actually find 7 new active compounds through a screening campaign. Just for acquiring sufficient compounds is probably over $70,000 if we think about a 1% hit rate, which could be very generous, and $100 per compound to acquire it. So again, going back and rescuing these valuable compounds. And then finally, thinking about combining it with generative chemistry methods to more effectively explore chemical space. This was a collaboration with the open source malaria project. They actually ran a competition using sparse anti-malarial data, built a model using the technology in Sorella, and then having validated that blind by the project team, a number of organizations were selected to propose new compounds using generative chemistry methods predicted to achieve the activity required by it. It's a novel mechanism of action here. The open source malaria team synthesized and tested those, and of the compounds suggested in this series, the only one that was confirmed to be active experimentally was that proposed by ourselves and our partners, Intelligence. Now, we think the reason that this worked is we did not propose the compound predicted to be most active. We proposed the compound that was most confidently predicted to be active. And taking that uncertainty into account gave us that high confidence we were going to deliver a successful compound. I love this quote. This is actually in the paper by the OSM team. The optimal intelligence session was thought by the human team to be a certain inactive. They kind of made it to humor us, really. Yet it displayed good potency and is a particularly useful outcome. They called this the machine overlords class of prediction. But essentially, it unlocked a new direction for this project that they'd previously discarded. And I've just provided you with a few examples. We've had the privilege and pleasure of working with many different organizations of all different sizes and shapes to apply these approaches across the sort of discovery pipeline. I will point you to our many publications and webinars that describe these with our partners at the end as well. So it's great to have an algorithm that works and delivers value. But as I say, we need to put it in the hands of the practitioners. So it's about automating this as much as possible, so you can connect directly with the data sources. It does the tedious and time-consuming but very important cleaning of that data, transformation into the right units to build good models. It populates this sparse matrix we've been talking about. It can build that imputation model. It can then fill in the blanks and offer the insights we've been talking about. And of course, as new data become available, it's automatically ingested, the whole thing is updated, so you're always working with the results based on the latest information, and you're avoiding that tedious and time-consuming burden of constantly building, validating, and updating those models. And those are made seamlessly accessible through our Stardrop software, but different ways you might want to visualize and work with those, the same information, so all of those, the same insights, the same results, the same models are available via a RESTful API. In the world of Stardrop, we make it really clear you can do a query for the compounds you're interested in. Where the data is available, it comes back, the experimental data, and it automatically fills in those blanks. You can use this for multi-parameter optimization. And then here you can see the blue squares are the imputed values, but this purple one is saying, look, I know you've measured this to be inactive, but based on all the other data you've got, that looks to be a false negative. Go back and check it again. So it just surfaces these results in a very transparent and intuitive way. So finally, the final stage here is, well, organizational change. And so I think what we're hearing a lot of discussion about, is that organizations really need to think about how to adopt these AI methods to stay ahead. But it is entirely appropriate to be skeptical. There's a lot of hype, a lot of claims being made without the evidence to back it up. So look for these methods that actually deliver real value in the context of drug discovery, not just a fancy headline. Of course, if we're going to use AI, we need to change the way we work. We need to be prepared to synthesize fewer compounds and perform fewer compounds. There's a natural tendency, oh, just make a few more compounds just to test the models right. Well, that's great, but then you can't come back and complain it's not reduced the number of compounds you synthesized. And we will be making and testing some compounds we otherwise wouldn't have chosen. Jan gave some really nice examples of that on the panel, that, things you wouldn't have thought of yourself, things to test and challenge the hypothesis that you have. Now, again, I think we've seen lots of examples of this. AI will not replace skilled chemists. That's not the goal of AI, because the combination of AI with that human expertise, that strategic understanding, is more powerful than either alone. It's this idea of augmentation. But I think it's fair to say that chemists who embrace these methods will have an advantage over those who do not. So if you want to talk about this more, come and have a chat at booth 10, visit our website. You're very welcome to email me. And then, as I say, all of this is published and presented publicly on this slide here. I'm not expecting you to write this all down. If you're really quick, you can get the QR code. But feel free to email me if you want a more detailed list or a copy of these slides. And in many cases, we've also presented these results in collaboration with our collaborators. And again, there's a QR code there if you want to access our webinars and listen to more talks. Not all by me. Thank you very much.